The recognition of problems, the understanding and definition of solutions, and the technological expertise to implement them depends on the skills and technical know-how of businesses such as Oleo. Advanced technology and design tools can realise safety improvements both in infrastructure and vehicle design. Oleo worked to understand the behaviour of vehicle structures and the effect of the collision forces at work to make the vehicles safer by controlling the energy released. This is done using in-house test facilities with simulation software to validate the test results. Oleo has developed simulation software to analyse collisions between single vehicles or rakes of vehicles to assess the energy dissipation. This reduces the need for full-scale impact testing and assists vehicle builders in complying with the EN 15227 standard for the crashworthiness requirements for railway vehicle bodies, where the validation process is now largely based on simulations. In the 1990s, research indicated that end-on collisions of railway vehicles presented the greatest hazards to passengers, and that most fatalities happened at speeds of less than 60 km an hour. Two distinct problems were identified which required engineering solutions. Firstly, the elimination of vehicle overriding or climb over, and secondly, the prevention of uncontrolled structural collapse by managing the energy dissipation. Understanding collision behaviour needs the latest technology, combined with years of technological know-how, which Oleo possesses. In the 1990s, vehicle builders were looking at solutions to these problems. This led to new cab designs and intermediate ends, combined with controllable characteristics, hydraulic couplers, and anti-climbing devices. It was predicted that these designs would eliminate vehicle overriding. The step to fully confirm these predictions was a big one. It needed a series of collision tests in controlled but realistic conditions, at impact velocities of up to 60 km an hour. 4 tests were to be staged. The first test would demonstrate the classic conditions for vehicle overriding. The second would validate an override design. The third test would be a preliminary low-speed collision to confirm low-speed behaviour prior to the final test, a high-speed collision between 2 rakes of specially modified vehicles to prove that controllable energy dissipation can take place. Computer-aided design, including finite element analysis and dynamic modelling, was used. Oleo carried out tests of the components designed to absorb energy in a controlled and predictable way, and their calculated performance was confirmed. New structures and panelling were added to the test vehicles, including 10 additional vehicles to form 2 rakes of 5. Oleo anti-climbers and hydraulic energy absorbing couplers were then fitted. Each test was to measure key parameters such as vehicle velocity, overall body end collapse force, longitudinal crash pulses, distribution of load, coupler forces and vehicle pitch. On the test day, cameras were placed in set locations using scaffold and platforms along the 20 kilometres of selected track. The first test was to show classic overriding. From the release point, a single vehicle approached a similar but stationary vehicle at 60 km an hour. On impact, the train overrides by 1.5 metres before settling. The high vertical forces caused the leading end of the impacting vehicle to lift and derail, causing damage to the vehicle and track. For the second test, the stationary vehicle was fitted out with a new cab end, Oleo anti-climbers either side on the buffer beam, and an Oleo hydraulic energy-absorbing coupler. When released, the vehicle's twin travelled towards the stationary car at 60 km an hour. The results are far less destructive than the first test, with all wheels of both vehicles remaining on the track and with the absence of any override. Controlled energy absorption, the use of anti-climbers and hydraulic couplers had just been validated as a means of preventing overriding. On the day of the final test, 5 vehicle test rakes took part in a test to check that the dynamic loads produced at low speed by 350 tons of colliding railway vehicles would act as predicted. The released impacting rake met its partner at 8 km an hour, which produced unspectacular results as anticipated. For the final test, the train arrives at the start point and final checks are carried out. The train then sets off and picks up the required speed before the release cable disconnects the test rake from the main vehicle. The test rake coasts the final 1 kilometre to the stationary vessel for the collision to take place. After the impact, the vehicle is inspected and signs of success are clearly visible. A controlled release of collision energy progressively absorbed all the way down the trains. Collapse is limited to defined collapse zones, with no damage to the main passenger carrying parts of the body, and no override or derailment occurred. The tests conclude that vehicle-to-vehicle override can be prevented practically and economically. Uncontrolled structural collapse can be prevented by managing energy dissipation on a whole train basis to provide increased safety to passengers and crew.